All right, welcome back. I will be discussing linear transformations in this video. The last video was on dimension of a finite dimensional vector space. But in this video, I'm going to be talking about linear transformations and discuss some very important theorems and examples in linear transformation. This is the beginning of module 2. Throughout this video, I'm going to be using F to denote the field that could be R or C, real numbers or complex numbers, and V, U, W, in most cases will be vector spaces over the field F. All right, so let's start with definition. Who is a linear map or a linear transformation? A linear map from a vector space V to another vector space W is a function, okay, written as T column V to W, meaning that V is the domain and W is the codomain. Satisfying these properties, one, whenever I apply this function to two elements from the domain, it can be written as T of U plus T of V. So T of U plus V equals T of U plus T of V for all UV in the domain V. And this is what we call additivity property. Additivity. All right. And the second property says if T is applied to some scalar multiple times U, I can pull out the scalar. So I will have CT of U for all U in V and C in this field. Once these two properties are satisfied, I'm going to say T is a linear map or T is a linear transformation. All right. Just on the side here, I'm going to just make use of this side. We are going to denote the set of all linear maps as this LVW. So is the set of all linear maps from V to W. So from now on, anywhere I write L of U or VW, I'm referring to the set of all linear maps from V to W. All right, I'm going to be looking at some examples very soon, but I just want to briefly mention these examples, which are trivial ones. 1, 0 is in L, 0 is here, all right, because I can F0V equals 0. And that satisfies everything we have. Also, example 2, identity map, it belongs to L of V, U. I want you to pay attention to these two examples because they will help us to show that this L is a vector space. Okay. All right. So, and this is simply because we can define IV to be V. So this is called zero linear map. And this one is called identity linear map. Linear map. All right. And here are very interesting examples. Show the following functions are linear transformations. One, if I take T, okay, from which is a linear map from PR into R. PR is the set of all polynomials, okay? And I define the function this way. This is a linear transformation. We can show this easily because integral of the sum of the function is the sum of the integral of the functions. So the same thing with differentiation. If we just take a function from P of R to P of R, from set of polynomials to set of polynomials, and define it as a derivative. Clearly, when you differentiate the polynomial, you get a polynomial. So it's not surprising that the codomain is this, okay? And this last one is called multiplication by x squared. When I define a linear map that is defined to be x squared times p for all p polynomial functions, and for all x and r. I'm going to need this last one later on and to show that something is not true. All right, I think you can take this as exercise to show that this is linear transformation, but I'm going to walk through the first and the last one. All right, so let's show that this guy is a linear transformation. So proof. Okay, so to show that something is linear transformation, and I'm going to be giving us some properties later, but for now, we need to first, so to show the first property, we need to take two polynomials. So let's call it P and Q from the set of all polynomials. I've seen this a lot, it's a vector space. And we want to investigate what is T of P plus Q and T of P and T of Q. So let's start from the left. So T of P plus Q, apply this to X. By the definition, here, by this definition, if you apply T to a polynomial, you get X squared times that polynomial. So T, this polynomial plus polynomial is a polynomial. So T applied to this polynomial, a series, a single polynomial, is X squared times that polynomial, which is P of Q, P plus QX. All right, so this is not strange because we know how to define sum of functions, which is basically polynomial in this case. So P plus Q applied to X is simply P of X plus Q of X. And then I open up the parentheses. So I'm going to have X squared P of X plus X squared Q of X. And who is this first guy here? By the definition is T of P applied to X. And this guy here, by definition, is T of Q applied to X. So the first property is true. So let's see the second property. It says when we apply, so let P again be from this vector space of our polynomial, and let's take C to be from F. All right, so we want to check what is T of CP, right? All applied to X. According to the definition, it should be X squared into CP applied to X. We know that this is a polynomial, so constant can be factored out. So we have X squared CP of X. And of course, C also can come out. So I have X squared CX squared P of X. Now, very clearly, we know who is this guy. By the definition of this function, it is TP applied to X. So we have C TP applied to X. All right, which is what we want. Since this function satisfies these two properties, we will say that the function is a linear transformation or a linear map, which is actually what this is, okay? But that's exactly what we're showing, that it belongs to this class of functions. All right, so I'm going to be showing some further examples to actually walk through different cases. All right, this should be capital T. The following statements are true for a function T from W to W. All right, so if I have, and this is very, very important, okay? And I'm going to tell you why it's important and how not to misuse it, okay? If T is linear, if T is a linear map, then T of 0 is 0. All right, and I want you to pay attention to this word then. This is not if and only if statement. It says if T is linear, then T of 0 is 0. This doesn't say that if T of 0 is 0, then T is linear. Be very, very careful. T of 0 equal to 0 does not necessarily mean that T is a linear map. Be careful. If T of 0 is 0, you could end up having T to be a linear map. You could end up having T not to be linear map. But if T is a linear map, then T of 0 is 0. However, where this is extremely important, because someone would say, oh, but my goal is to show that T is linear. So why is this useful then? Yeah. When you want to show that T, when you are not sure whether T is linear or not, what is true with this property is that if T of 0 is not 0, then T is not linear. So it's actually very useful to show that some functions are not linear, okay? If T of 0 is not 0, then that T was not linear in the first place, because if it was linear, T of 0 would be 0. So this is very, very important to take note of. And I advise my student most of the time, whenever you have a function to show that it is a linear map, it doesn't cost much to check T of 0. And if T of 0 is 0, nothing to conclude. You move on. If T of 0 is not 0, then you can stop and say, oh, T is not linear. This is a very important concept here. All right. If T is linear, then this statement is if and only if. We can, instead of showing those two properties, T of U plus V equals to T of U plus T of V, and T of CU equals CT of U, we can simply combine the two together in this way. So T of CU plus V is the CT of U plus TV. I'm not going to prove some of these properties here, but they are quick exercise to check. So in some cases, or most of the cases, we'll use this one to show that something is a linear transformation. And lastly, if T is linear, if and only if for this set of vectors in V and this set of constants in F, we have that the T of the sum is the sum, T of the sum of AIXI is the sum of AIT of XI. You can put in T into as many as possible. Since we say that T of U plus V is T of U plus T of V. In fact, it is true that if you have many, let's say 3, it's still true. You can distribute this. And as many as you want up to some n. All right? Now, let's get to some proofs, okay? And this is very important concept that we are going to use for some example later. Suppose I have this set of vectors is a basis for V, and this simply should be the subsets. This should be a subset, not an element. All right, there is this a unique linear map T from V to W such that TVJ equals to WJ for each J 1 to N. So let's try and prove this here, because this is very, very useful in application. To solve many examples, you will need this idea. So it says there is this a unique linear map, okay, that takes VJ, each VJ to WJ. Okay, proof. All right, first, let's define the function. For now, we don't know who is this guy. It comes from V to W. I'm going to define this function by, I'm going to have T of C1 V1 all the way to plus Cn Vn equals to C1 W1 plus all the way to Cn Wn. Okay. Where the C's coming from the field. Okay, the arbitrary element in the field. I don't even know if this function makes sense, because when you define a function, you need to know whether it is well defined. Okay, is it well defined? I think so. Remember that B, okay, is a basis. So B equals V1 all the way to Vn, okay? Those V's, let's call it B. It's a basis for V. It's a basis for V, right? And if it's a basis for V, it spans V. It means that any element I take from V, I can write it as a linear combination of all these V's. So this guy here is an element from V. So I can take T of this guy to give me some elements a linear combination of the vectors in W. Remember that the W is a vector space, okay? W is a vector space. So this linear combination, since each Wi belongs to W, then the linear combination also belongs to W, okay? Being a vector space. Good. And of course, the well-definedness means that we know that since B is a basis, okay, each element of V can be uniquely written in the form of this linear combination. And I think that is the major point here. Since B is a basis, each of element I take, so if you let V be in V, I can uniquely write V as a linear combination of all the VI's, because B is a basis. All right. Okay, now that I have a map that is written this way, it is well defined. I just showed that this is well defined. For each J, okay, can I take Cj to be 1 and others, okay, other C's, other scalars equals 0? I can do that, okay? And once I do that, I'm going to get T, because if the only term that survives in this linear combination is the Vj, the rest will be 0. Cj is the only one that is 1. So I'm going to have Vj, and then the same C is used to define the right-hand side, so Wj will also survive there. So it seems that I have something that I am trying to prove, okay? T is, this T gives this kind of property. So I have a well-defined T, and that T of Vj is Wj. Now I have two more jobs to do. One, I need to show that this T is a linear map. There is nothing that I've shown that is a linear map yet. And secondly, I need to show that it is unique. So let's start with to show that it's linear map first. All right, to show that T is a linear map, so claim 1, T is a linear map. Okay. T is a linear map. Is a claim yet. We want to show this. So first, we want to show that if we take two vectors, uv from v, we want to show that tu plus v is tu plus tv. All right, now u is coming from v. Okay, u is coming from v, b is a basis. It means that there exists some constant Let's call it A1 up to AN. That is for U. Let's call the one for V to be B1 up to Bn. All these are scalars such that U can be written as linear combination of the basis elements. A1 V1 plus all the way to AN Vn. The same thing with V. V can be written as the linear combination of the basis elements. What is giving us power here is the fact that B is a basis for V. So this can be written uniquely this way. All right, now let's find T of U plus V. Before I do that, I'll quickly find U plus V. This is just vectors. So U plus V will simply be, I'm adding A1 V1 plus B1 V1. So I can combine the constants, the scalars for V1. I do the same for all of them. The last one will be AN plus BN V. So it makes sense if I'm applying T to the sum, I'm simply applying T to all this guy. A1 plus B1 times V1 plus all the way to AN plus BN times VN. Okay. By the definition of the T that I define when I have T of some constant V1 up to some constant Vn, the same constant times W. So I'm going to have A1 plus B1 times W1 plus all the way to AN plus BN WN. Remember that is how T was defined. I can remind you from here. T takes C1 plus C1 V1 up the way to Cn Vn and then produces these vectors, but the same constants, okay? W1 is introduced up to Wn with the same constant as that of the linear combination we chose from the domain. All right, now that I have these sections, I can simply break this into two. It's a vector. So I'm going to have A1 W1 plus B1 W1 plus all the way to AN WN plus BN WN. All right, I can rearrange this to have A1 W1 all the way to AN WN, and I can group this one side plus the ones with B now. So B1 W1 all the way to BN WN. And very clearly now we can see that this guy here is T of A1 V1. That should be U1 all the way to AN UN. No, excuse me, it's the same V1 AN VN. Plus, and this one is T of B1 V1 all the way to BN VN. Okay. Lastly, T of this linear combination is what we actually call T of U. And T of this linear combination is what we call T of V. So the first one, the first property is satisfied. And you can combine this property as well, but just to not mess things up because of different constants, that's why I'm doing it separately. So the property 2, so we take U again from V, and we take the constant. Let's take lambda, in this case, lambda to be from F. And now we want to check is if T of lambda U is lambda T of U. So to check this. All right, U is coming from V. It means that there is still some constant. So let's use the same constant as we have before. So U can be written as the linear combination of the basis elements. So we have A N V N. And now when I apply lambda, it means that lambda U will be lambda A1 V1 plus all the way to lambda AN VN. So now it makes sense if I'm applying T to lambda U, which is the same thing as T into lambda A1 V1 all the way to lambda AN VN. Based on the way I define my T, when it takes linear combination like this, this is now the constant. Okay, and it produces the same constant, but now with W. So I have that all the way to lambda AN times VWN. But these are constant. Lambda is common to all, so I can pull out the lambda. So I have A1W1 all the way to ANWN. So lambda is just a scalar here, can be pulled out of the whole equation. And then again, now I find myself with this, which is nothing but T of A1 V1 all the way to ANVN. And that is what I call T of U. So you can see now that T belongs to this guy. T is a linear transformation or is a linear map. So I've shown the first claim. The second claim is the uniqueness, okay? So uniqueness of this function. I'm kind of discussed that when I define that thing, okay? Because the uniqueness actually is coming from the uniqueness that you can uniquely define a vector in V using that basis. So suppose T belongs to this, which we have shown actually. And we have also shown that T of Vj equals to Wj for each j 0, 1, sorry, it starts from 1. One, 2, all the way to n. Let's see 1 all the way to Cn be scalar. The homogeneity, okay, of T implies that T of CJWJ, sorry, TJVJ is exactly CJWJ. Again, for each j. When I take V, I can write it unique. Okay, so in other words, homogeneity of T, because we've seen that we know that T of CU equals to CTU. So that property allows me to do the same for each element by this. That is the first thing. The additivity, okay, of T, additivity property of T implies, okay, that it's not happening only for CJVJ, it happens for everything. So it happens for everything, C1, V1, all the way to CNVN, producing C1, W1, all the way to CNWN. In other words, T is uniquely determined on the span. T is uniquely determined. It's the span of those V. Because that's what I just discussed now. If that is the case, okay, we know that B is a basis. So since B is a basis, B is a set containing all the V's. This implies that T is uniquely determined on V. Let me recap what I've just discussed here, okay? Suppose T is a linear transformation, and we've shown that already, okay? And TVJ equals to WJ for each J. If I have all the C's in scalar, the homogeneity property of T allows me to do this, okay? And then additivity property of T allows me now to extend it to the entire linear combination. So it makes sense to give T in this form, okay? And this definition means it makes sense, okay? Because I can always do this. I can anything I have. This linear combination is possible because of the span, okay? So T is uniquely determined on the span, okay? All right, if that is true, I don't know if it's on the OV, but the fact that B now is a basis, okay, is a basis for V, I can move from the span to the entire V, okay, because it's a basis. So that concludes the fact that we can always find a unique T from V to W such that T of Vj equals to Wj. I'm going to show you, most importantly, how to apply this theorem before the end of this video, okay? All right, so let's define some notions, okay? Definitions now. Suppose I have two linear maps, okay, from V to W. and I have a scalar lambda. Now I'm going to define the sum of these linear maps, T plus S, and the product the scalar product actually, lambda T. These two, the sum and the scalar product, are also linear map. From the same domain V to W, and they are defined this way. So S plus, or T plus S, whichever. T plus S applied to a vector in V is going to be TV plus SV. And lambda T applied to a vector V would be lambda T of V. Okay. For all V in V, for all V in V and the scalar. All right, with this definition, with this operation, we can say that the space or the set of all linear maps from V to W is a vector space. I want you to check that on your own. Check it out. With these operations that I've defined, is addition and scalar multiple. Addition and scalar multiple. I want you to check it. It's a good exercise. All right. More definitions. So another one. Okay, so if I have a linear map from W, from U, okay, vector space to V, and I have another linear map from V to W, then the product ST will be a linear map, okay, from U to W. It's going to be defined as, so it's ST moving from U to W, and ST applied to a vector in U will be S applied to T of U for all U in U. And this is like a compositional function. Okay. Be very careful. You can see that the codomain here is the domain here. And it's not the same when you have TX, so be very careful. It's ST, not TS, the other way around. Because L is a vector space, you can get so many properties. For example, T1, 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 T2 times T3 is T1 into T2 times T3. Okay. So expected that this T1 up to T, they are linear transformation, and the product makes sense. Okay. Not all the time this product makes sense. You have to choose the domain and the codomain such that this product makes sense. And we have several of these type of properties. Another one, which I can quickly give, is if I have S1 plus S2, this is a linear transformation, and I multiply that with T, it's going to be S1T plus S2T. And if you have it the other way around, S times T1 plus T2 is going to be ST1 plus ST2. In this case, T1, T1 and T2, there will be a linear transformation from U to V, and S1, S2, in order to make sense, will be V to W. But in this first property, you have to choose the domain such that this product makes sense. Very, very important. All right, so let's go into some example. Now this says, determine if the following functions are linear transformation, justify your answer. So I have a map T3 from R3 to R2, and it's defined this way. Now, like I said, it doesn't hurt to check T of 0. So T of 0 here is the same thing as T of 0, 0, 0, means that X1 is 0, X2 is 0, X3 is 0. So you will have, by this definition of T, you will have 0, 0 minus 0, which is 0, 0. Implies no conclusion. I cannot make any conclusion because T of 0 is 0. If T of 0 is not 0, I can conclude that T is not a linear map. All right, in that case, since we have no conclusion, we go ahead and prove those two properties. So I'm going to use the combined one, and that will be, so I'm going to let XY from R3 and a scalar, let's say lambda. So X is from R3 means I can write X as X1, X2, X3, and Y equals Y1, Y2, and Y3. All right, so first I would like to know what is lambda X plus Y. This is just a vector addition in R3, so I'm going to have lambda times X1, X2, X3 plus Y1, Y2, Y3, and that will give lambda X1 plus Y1, that's the first component, lambda X2 plus Y2, and lambda X3 plus Y3. So it makes sense now to say I want to apply T to lambda X plus Y, which is T of lambda X1 plus Y1, comma lambda X2 plus Y2, comma lambda X3 plus Y3. All right, so let's check. Now, I want you to understand the definition. It says whenever I take 3 component Y's like this, the answer is in 2 dimensions. And the first element here is the same first element from what I applied. And the second element is the difference between the x2 minus x3. So here, the first element here for me is the same. So I'm going to have lambda x1 plus y1. And the next element says you have to subtract, you have to have the middle guy minus the last guy. So the middle guy for me is lambda x2 plus y2 minus, now be careful because the negative will affect everything. So put the parenthesis, lambda s3 plus y3. Probably put the parenthesis here too. And this means what? I can still have lambda x1 plus y1. Now I can rearrange this one to be lambda x2 plus minus lambda x3, not a common. That is one component. I just rearrange plus, then I take the one with y2 minus y3. Okay, so I can break these things into pieces. So this is just vector addition. So I'm going to have lambda x1, comma, the first component here with this guy, the first component here. Lambda x2 minus lambda x3 plus the first component here and the last component here. So that will be y1, comma, y2 minus y3. Okay, so if you notice the first vector here, lambda is common, so I can pull out the lambda. I have x1 in comma x2 minus x3 plus, and y1 comma y2 minus y3 based on this definition. This definition here, whenever I have that, I'm going to reproduce the left-hand side, which is just t of y. Probably I should do that in the next slide. So I don't stop here. So I started from this, and I end up in what I call lambda into, so let me backtrack a little, lambda x1 comma lambda x2 minus lambda x3 plus y1 comma y2 minus y3. And again, lambda is common here, so I pull out the lambda, so I have x1 comma x2 minus x3 s2 minus s3 plus y1 comma y2 minus y3. And based on the definition, again, this one here is t of x, and this guy here is t of y. So since I'm able to show that, then t is a linear transformation from R3 to R2. Right? Next question. So we have T2 now, which is R3 to R2 by this definition. It's just slightly different. So again, doesn't hurt to check T of 0 to see what happens. So T of 0 here is the same thing as T of 0, 0, meaning that x1 is 0, x2 is 0, x3 is 0. So let's plug in those zeros here and check. So I'm going to have S1 is 0 minus S2 is 0. Then 3 plus S3 is 0. And now I have 0 minus 0 is 0. 3 plus 0 is 3. Definitely this is not 0, comma 0. And you see, I do not have to proceed further. I can conclude here. Since t of 0 is not 0, then t is not a linear transformation. This t is not a linear transformation. Very straightforward. Another example. So we have a function here from set of n by n matrices, okay, into set of n by m. Remember that there is a change of order here. All right, it's defined to be, when you apply t to a matrix A, you get the transpose of that matrix. So we want to show that t is a linear transformation. So let's prove that. Again, I'm going to use the combined properties. So let's take A and B from the matrix m by n. And let's take some scalar lambda. And we want to show if t of lambda A plus B is lambda t of A plus t of B. Now, by the definition, T of A gives A transpose. So T of the entire of this guy is a matrix altogether. So T of that matrix is that matrix transpose. So A lambda A plus B transpose. Now, remember that A plus B transpose, the property of transpose says you can distribute the transpose. So A plus B transpose means A transpose plus B transpose. So lambda A plus B all transpose is the same thing as lambda A all transpose plus B transpose. Now, again, when I have a constant with the transpose, the constant comes out without the transpose. So of course the transpose doesn't make, this is a scalar. So that means I have A lambda A transpose plus B transpose. A transpose gives TA by the definition of the T we have here. And B transpose gives TB. And that's exactly what I need to show. So hence I can conclude that this T belongs to the linear transformation. Write it in the last line. This belongs to the linear transformation, set of linear transformation from F to Mn. Okay. Next example. Okay, so this is more of theorem. So suppose I have set of linear maps, okay, from V to W, and B is a set of vectors. All right, V is a set of vectors in V, such that B star, which is TV1 up to TVN, is linearly independent set in W. We want to show that B is linearly independent set. Okay. This is very, very important. I'm going to show you the usefulness in the subsequent lectures. Okay, so for us to show that B is linearly independent, okay, to show that B is linearly independent, To show that B is linearly independent, all we have to suppose, okay, is if there are, so suppose there is some constants, okay, scalar, such that the linear combination gives 0. So C1, V1, all the way to Cn, Vn is 0. We need to show that all the C's are 0. That's the goal. In order to show that this B is linear transformation. Okay, so I'm going to repeat this equation, which is given this way. We have this, but we just want to show that C's are 0. Now, remember the theorem I proved before. Now is the time to use it. I can apply T to both sides of this equation, okay? Remember that T is a linear transformation, so and I think is missing here. T belongs to L here. Suppose T belongs to L. That's a typo. So T is a linear transformation. So I'm going to apply it to both sides to get T of all this guy in the left is the same thing as T of 0 in the right. All right, remember that if I apply T to this linear combination, I can apply it to individual one. I can put out all the C's, the property 3 I showed when I was talking about some of the properties for linear maps. So this is actually the same thing as C1 TV1 plus all the way to Cn TVn. All right, but T is also linear transformation, means T of 0 is 0. So this is true. I would just advise you simply recall that this is what you are using. Oh, can you recognize this guy? This is a linear combination, so take this as some vectors. This is a linear combination of the vector from B star. But we know that B star is linearly independent set in W. You have a linear independent set, you take the linear combination, okay, equal to 0, then all the C's have to be 0. So since B star, and it's always good to remind yourself what is B star, is linearly independent, set in W, because T of something makes sense inside W, then C1 to Cn equal to 0. That's exactly what we want to show. So hence B is linearly independent. In V, set in V. So you can see how we use the assumption in this case. This is very, very important. How also that we are able to use the last theorem that I proved before this. Now, let's combine all these theorems now in this case. These are more examples. All right, so prove that there is a linear transformation T from R2 to R3 such that T applied to 1, 1 is 1, 0, 2, and T applied to 2, 3 is 1, minus 1, 4. And in fact, we want to know what is T of 8, 11. Remember that we don't know explicitly what is T. We have no idea. But the first theorem I proved shows us that we don't even need to have the idea of what T is explicitly. We just know that if we have a basis and I apply T to each vector in the basis, I can get another vector in the codomain, in the domain. All right, so let's look at this together. So solution. First of all, since I'm applying T to some Vj, so let's take this one to be V1. So let's V1 now to be 1, 1, and V2 to be 2, 3. All right, so let's put these guys in a set, V1, V2. The first question we have to ask is this a basis for R2? We need to have it to be a basis for the domain, okay? Is this a basis for R2? First, to be a basis, we need to show that it is linearly independent and spans the whole space. All right. Clearly, okay, V1 is not multiple of V2. It's not multiple of V2. And V2 is not multiple of V1. That is, there is no scalar that I can multiply with 1, 1 to get 2, 3. No such scalar. Hence, that's all you need to defend yourself to say that B is linearly independent. Okay, B is linearly independent. What's the dimension of the domain here? The domain here is R2. The dimension is 2. You have a linearly independent set with length 2, which is the same thing as the dimension of the vector space. You don't have to show that it spans. We can conclude that B is a basis for R2. Let me repeat myself. I put all these because I want to use the theorem that says TVJ equals to WJ. That's all I'm trying to get at here. And these VJs, they are the vectors from the basis. So first I have to put them together and show that it's a basis, which we just showed. When I have two elements in the basis, the dimension of the vector space is 2. All I have to show is either to show that B is linearly independent or spans of B equals to R2. Okay. In this case, it is very easy to show that B is linearly independent because it involves just 2 vectors. So one is not the multiple of the other one. I don't know any constant that you multiply by 1, 1 and you get 2, 3. So clearly that is not possible. Therefore, we do have this happening. So B is a basis. Now that I know that B is a basis, I know that T of V1, I know that B is a basis, so T of V1 is some W1. Okay, so this implies that for this case, W1 for us is 1, 0, 2. And T of V2 is some W2. In this case, it means that W2 for us is 1, -1, Okay. So such T exists by the previous theorem. And it is unique. All right, so let's find T of 8, 11. If this is true, then T of 8, 11, you should be able to find it. In order to find T of 8, 11, we need to first show that 8, 11 belongs to the span. So since V1, V2 is a basis, so 8, 11 has to be in the span of B. And so we need to find those constants. So suppose we have A V1 plus B V2 equals to this guy, which is A into 1, 1 plus B into 2, 3 equals to 8, 11. If you open up this, you will get system of equation A plus 2B equals to 11. A plus 3B equals to, sorry, A plus 2B equals to 8, A plus 3B equals to 11. This is a very simple simultaneous equation, two equations that you can solve. You will get A equals to 2 and B equals to 3. Now I can plug them into, I can check, so 2 times 1, 1. Plus 3 times 2, 3, certainly is 8, 11. All right, apply T to both sides. I have T into 2, 1, 1, plus 3, 2, 3, equals to T, 8, 11. So T, 8, 11 is what I'm looking for, okay. Let me put it in the left. And then T of a constant times a vector means 2 of T of 1, 1 plus 3 of T of 2, 3. But we have been given that T11 is 1, 0, 2 plus 3 into T23 is 1 minus 1, 4. And so you can open up this, you can multiply through and have 2, 0, 4 plus 3 minus 3, 12. And if you combine everything together, you get 5 minus 3, 16. And T of 8, 11 is 5 minus 3, 16. And these are the beautiful applications of those theorems. I've shown you some in the proof of the previous theorem that I just showed, and this is another example, and much more of this will be in the next lecture, okay? Because of time, I don't want to go beyond this. Please watch through, take notes, and if you have any questions, ask. I will try my best to answer your question. Thank you very much for being patient to watch the long video. See you next time.